Maybe I should put a D2L announcement out there saying that we're back, right? It's good to see everyone's faces finally. Of course, the day after I leave, they decide to take the mask mandate off. Hopefully it doesn't come back. Cross your fingers. I did want to just spend a little bit of time kind of going through what I talked about last week because, you know, there was quite a bit of information. We're actually a little bit behind, probably half a week behind on the material in general. So hopefully we can kind of just talk through some of this and maybe it'll help. I'm going to issue a homework this probably today or tomorrow, which will be due next Thursday, okay? And then you'll have a quiz next week. So this week was kind of a bye week, all right? Just because the material didn't line up, okay? So we're gonna have homework that's gonna be all about columns and then some torsional shear stress and torsional displacement stuff, which we didn't go through any examples last week. So today, hopefully we'll get through some examples so you'll have everything you need to start doing the homework. All right, so as it relates to columns, all right, I went through kind of a lot of information about columns, well, the entire section of columns, okay, in the text, chapter 16. And the big takeaways to think about here as we go through the homework and you guys go through the quizzes is really it's a super undesirable failure mechanism, right? As a designer, you wouldn't want buckling to happen. One, it's very catastrophic, right? It's very, yeah, I mean, it does not have, provide a lot of warning, right? When it buckles, it's done, right? You have zero, right? It's the unstable condition, right? Where if that column were to buckle just slightly, right? It's coming to the ground, right? It's not like we can see it as it goes. It's very catastrophic. And so it's a very undesirable failure mechanism. And so we want to make sure that we analyze it and compute what the capacity of our columns are precisely, right? As closely as we can. And then obviously we're going to add factors of safety in the real world to account for the fact that this is something we don't want to see, all right? And so the big takeaway I wanted to get out of this is, right, fixity at the top and the bottom, a change in fixity, essentially changes the calculation associated with the capacity, right? And obviously as you add stiffness, right, or restraint, so this is our pin-pin column, which I mentioned in the lecture, that this is the original Euler equation that was derived, was for this pin-pin case, right, this idealized case. But as we start adding fixity, maybe it's a fixed pin or a fixed condition, okay, we are essentially reducing the length of our column, right? And so that's where we end up getting this K factor, this effective length factor, which starts to go down, right, reduce the effective length of our column based on having fixity. Similarly, if we reduce fixity from our pin-pin idealized case, right? If we get rid of, right, if we do a cantilever, for instance, right, we end up increasing the overall length of our column because we don't have that fixity, right, at the top or one end. And so we end up having to double the length of the column in order to account for the fact that we don't have the extra fixity, okay? And so going through the homework, right, in the real world, you would look at a column and look and analyze its fixity, right, the top and bottom, to decide, okay, what is the effective length of our column and what values would we plug into our, right, P critical and sigma critical equations in order to get capacities out of it, all right? One thing to also note, right, excuse me, in the real world, and I tried to highlight it in the lecture, was, right, if we have a column, so this is a W-shaped column like we went through in the notes in class, right? There's tableized values for these. This would be like a W10 or something like that, okay? 10 being the nominal depth, so from the top of this beam to the bottom of the beam, nominally is 10 inches. Is that the real thing? No, okay? As you get different sizes of members, okay, so we went through, this for instance was for channels, right? So it's a C15 by 50. And so there's a class of channels that are all C15s, right? In this, it's showing the depth is 15, but in reality, it changes just a little bit based on, right, that last number being the weight per foot. So if I cut a section of this W10, right, this might be a W10 by 30, it would weigh 30 pounds if I had a foot of it, okay? And so, especially with wide flange columns or even channels, as we noticed in the example when I went through it in the lecture notes, right, the resistance for this section to buckle is different in one direction, right? If this were to buckle vertically, right, versus buckling side to side, right? So this thing's sitting here, and if it wanted to buckle one way or the other versus back and forth, it's going to have a different capacity, right? And so we want to be mindful of not only the difference in mechanical properties, right? Our moment of inertia, I, plays a big role, okay? E plays a big role. Usually, though, the column is all the same material, so E should be the same in both directions. But the I changes. And then on top of that, in the real world and in the homework I'm going to give, right, we can have different restraint conditions in two directions, right? We could have a column, say that column, right? We decided that they wanted to put a column in the center of this room, and we stuck it right here, extended from the desk to the ceiling, okay? Well, if it was sitting like this, right, we could want to, we might want to restrain it maybe halfway up in the weak direction, right? And then in the strong direction, maybe we won't put anything perpendicular to that, right? So we would tie off to the walls on both sides to essentially keep this column from being able to move side to side halfway up. And so then that affects what we do with respect to our effective length, right? KL over R, that changes from the weak axis to the strong axis, yeah.
In those videos you talked a lot about like the buckling in the Y and buckling in the X, and I was a little confused on like what that looks like in real life.
So like buckling in the X direction, right, would be moving this cross section along the X axis, right? So if I had this cross section, it was sitting up here like this, right? And so buckling in the X direction would be that this thing's moving side to side like this, right? And moving side to side like this means that this section is rotating about the actual Y axis, right? Does that make sense? So it's kind of a fairly detail-oriented with respect to making sure that you are analyzing it appropriately to know that, is it buckling in the weak direction? Well, if it's buckling in the weak direction, right, this thing's rotating about the weak axis. And if it's rotating about the weak axis, this column is going to be buckling along the x-axis. Does that make sense? I tried to find a big yardstick before I came here today, but I couldn't find one. To kind of show you like the buckling shapes and stuff like that too, but does that kind of help? Sort of, right? Like when we went through our example, right? These two channels that were sitting next to each other, right? They could buckle vertically, right? That'd be essentially taking this column and it would be moving in and out of the page. And then they could buckle side to side, right? And when they buckle side to side, they've got to bend, right? And when they bend, when they go side to side, they're bending about the weak axis, right? This y-axis. And then if they buckle in and out of the page here, right, they're going to be rotating, because they got to rotate in order to buckle. And when they rotate, they're going to be rotating about the strong axis, or the x-axis, but they're actually moving about the y-axis. Okay.
So those X and Y's are, we're looking at the cross section.
Yeah.
Okay.
Yep. Any other questions about columns? Right. So knowing that, right, this is one of our equations, we need to make sure that when we figure out the critical load, right, if you put a load on this column is just way too short. Right? If I put a load on this cross section, right, I want to know what is the modulus of elasticity. Well, that's based on the material. In this case, we're using steel. Okay. The The moment of inertia, well, that moment of inertia is going to be tied to which direction are we looking at buckling, right? And which direction we're looking at buckling is also tied to this effective length factor, right? KL. K is going to be based on what kind of boundary conditions, or how is our column fixed, right? Is it pinned at the base? So when it hits the desk here, can it rotate? But then it can't translate, right? It's just pinned here, okay? It's like the, it's a pinned pin case. If it's fixed, right? So it can't rotate or translate, right? That's going to change our K factor there, depending on what's going on at the top of the bottom. And then that L value, well, that L value is also attached to which direction is buckling. So you kind of have to keep track of what's going on. Any other questions? No? All right. So those were columns. Then we started talking about torsion. And I assume all of you kind of blacked out when I got to this point here, right? Started deriving what was going on with respect to rotations and angles of rotations and how the rotation of our shaft, right, the torque applied to the shaft relates to how far that shaft rotates as we go along, right? I don't expect you to know a whole lot, right? Don't have to keep a whole lot of that in your head. The big things out of this is to say, okay, we have a relationship, right? We have a relationship between the shear stress applied and the applied torque. Right? We came up with this relationship here. So if you had a shaft and you have applied torque on it, right? That shaft has mechanical properties, right? It has a polar moment of inertia, we call it J. And that's essentially the same as a moment of inertia, right? The moment of inertia is the resistance. It's essentially the resistance, of a cross-section to rotate, right? We have I sub x and I sub y, right? Rotation about the weak axis or the strong axis. Well, J is essentially the same thing, but it's how resistive is this section to rotation, right? And we're not going to go into open sections like a wide flange. In this class, as I mentioned, we're only going to be talking about cylindrical shafts, so hollow like pipes or solid round stock, okay? Makes things a bit simpler, okay? So if we have an applied torque on a shaft, right, the shear stress, the maximum shear stress, right, is a function of the polar moment of inertia, the maximum radius, we call it C, right? If we go back to this, C was our maximum radius. As we noticed through this derivation, right, because our angle of rotation increases as we go from the center. If you took the center of if you took a shaft and you're twisting on it, the center of that shaft doesn't twist, okay? It's only twisting based on the radius, right, and how far we go out. And so if we know that there's a relationship between deformation and stress, and so that's where we end up getting this linear change in stress as we go from zero deformation in the middle to our maximum deformation on the outside. So using that relationship, we say, okay, the maximum stress is on the outside. We have this polar moment of inertia, J. We can relate torque. Okay, we could figure out what the torque is if we knew the allowable shear stress, right? And the maximum radius and the polar moment of inertia. Or we could figure out what the maximum shear stress in our cross section is if we knew what torque we're applying, right? And then we knew the maximum radius and the polar moment of inertia, okay? And similarly, if we wanted to look at any shear stress at any point within the cross section, we can go back and relate it to, well, what is the shear stress at some given radius rho? That's what this is. Right? So we have these kind of big three equations, right? If we wanted to know what the shear stress was at some radius rho, we can relate that back to the applied torque, okay, based on the radius of that point, right? The applied torque and our polar moment of inertia, okay? Clear as mud. Any questions about that? You guys got it. You guys are experts now, right? Well, what's this polar moment of inertia? Well, again, as engineers, right, I showed you up here, it was this crazy integral of the radius squared over the area. It's like, screw that. We as engineers don't really care about, or we don't like to do integrals. Okay, I don't like to do integrals. So what do? Well, we have predetermined or predefined equations that were developed for the polar moment of inertia. So as I mentioned in this class, we're really going to be focusing on, right, circular shafts. So one type would be a solid circle or a solid shaft, right? We would have a radius, right, and a diameter associated with that solid shaft. Well, they tell us that the polar moment of inertia is pi over 2 r to the 4th or pi over 32 diameter to the 4th, right? And when we think about polar moment of inertia, it's really the polar second moment of the area is what this is called. Right. Our units here, if we looked at that equation, right, pi over 2 r to the 4th or d to the 4th. Well, the units for our equations here are going to be, say, inches to the 4th, right? Millimeters to the 4th. Those should be the units that we get out of this. Similarly, if we look at a pipe or a hollow shaft, right, we would have a outer radius, which we would call big R, and a inner radius, which would be a small r. Similarly, we could say we have a inner diameter of a small d and an outer diameter, big D. And because we're engineers and we're lazy, someone else has done this for us. And they say that the polar moment of inertia with respect to the radiuses of our pipe or our hollow shaft is pi over 2 big R, right? The outside radius minus the inside radius to the 4th minus pi over 32 d to the 4th minus d to the 4th. Right. Remember your order of operations, right? You're going to take our radius or our diameters to the 4th power first, right? Yes?
For the solid circle, is that a minus sign, not an equal to sign?
Oh, boom. Other way. Thank you. Thank you.
Where?
This was a minus sign right here,
Oh.
not an equal sign.
That's a minus sign?
No, it was. Wow. It's really going downhill, okay? This was a minus sign, and now it's an equal sign because that's what it should be, okay? You either use the radius of the shaft or the diameter of the shaft, right? Never should you be calculating the polar moment of inertia using both the radius and the diameter. You either use the radius or you use the diameter, okay? I'm just giving you two options here, okay?
Effectively, if you did that, you would just get 0, right?
Yes, you would. Well, yeah, if you did the entire equation, it should be 0.
So you figure it out pretty quick.
I would hope so. I would hope so. Okay. Well, we know from mechanics, right, when we've gone through axial systems, we really enjoy looking at displacements, right? So we really want to look at displacements for our torsional shafts, for torsional systems also, right? So torsion on shafts. So we really want to look at how does the applied force, which in our case for torsion is the torque, how does that relate to the rotation, right? We've got a rotation or a twist. As this shaft has an applied torque on it, right? We're rotating it. It's going to have some sort of strain associated with that rotation. And so if we have a strain, we're going to have displacement. So when we look at axial systems, right, we had this delta equals the force times the length of our axial rod divided by the area times the modulus of elasticity. Well, we want to figure out something very similar to that. Well, similarly to what we did here, right? We just took Hooke's law and we applied the relationship we knew for strain, which is the change in displacement over the original length, right? Delta over L. Then we took stress, which we knew was F over A, right? And so we essentially took our Hooke's law equation and we just plugged in the equations for stress and strain. Well, in this case, we're going to do the exact same thing. But instead of having sigma, right, up here we had sigma equals E epsilon, right? Modulus of elasticity times the strain. I showed you in chapter 4, we related, well, what's the shear stress relationship? Well, it's very similar. You have the shear stress equals the modulus, or the shear modulus times the shear strain. Well, we can plug in some things here. We can say, okay, the shear stress from up above, we know that the shear stress at any, I'm terrible at rows here. The shear stress at any radius rho, right? So tau of rho equals the applied torque times the radius with which we're looking at all over this polar moment of inertia, right? Well, shear strain is a little bit different, okay? It's not as easy as just saying the change in length over the original length. Hopefully, so you guys don't black out, I'm just going to give this to you, right? I'm going to say the shear strain based on, if we went back to our derivation and we looked at that small little sliver of our shaft and looked at the fact that it rotates, right? It displaces, right? The shaft is displacing every little slice of this shaft, as you can see, right? It's rotating, and every little bit of rotation adds up to this final rotation at the end. So if we looked at it, we would say that our strain is equal to the radius, right, at some radius, times d, right, the change in rotation over that small length. We get this rho d phi dx. And so this is angle of rotation per unit length. Saying like every one of those little slivers, right? If we had a 10-inch long shaft and we looked at it, every inch of that shaft as we went down the shaft would have some little bit of rotation. That would be our d phi dx. Okay. Well, if we plug those things in, okay, and we integrate, which none of us like to do, we're going to say that our angle of rotation, right, in radians equals the torque times the length divided by our shear modulus times the polar moment of inertia. if you went out to D2L in the appendix, okay? Under our, the appendix A, which is all of the main equations for this entire text, okay? This entire class, this guy is out there, okay? As I mentioned, right, this is in radians, which is really unitless. Not in degrees, but in radians. If we were looking at this equation, it's really only valid for a number of things, right? It's only valid for a constant material property or our shear modulus, right? If the shear modulus changes along the length of our shaft, well, we can throw this equation out the window, right? Because now you're not going to have this consistent adding up of our displacements, right, or rotations as we go along the length. The other one is it's got to be prismatic, right? We can't start with a pipe and then tack onto it a solid shaft, right, halfway through some length and expect this equation to work at the very end, right? Because your J is going to change as you go from one end to the other. Yeah.
That thing that on the left side of the equation.
Phi.
Okay.
That's
Is that
thing.
for the angle of rotation or change of angle of rotation?
That is the angle of rotation. Right. So if you wanted the, say, the actual rotation of a shaft, you would multiply that by the radius, and you would get how far has that point, right? If we took, I'm going to bring in like a little noodle or something, okay, for Friday, but if you were to rotate that noodle, like think about a pool noodle and you put your hands on both ends of it and you try and rotate it, right? This is going to calculate the angle over which, say if you held one hand fixed and you twisted the other hand of your pool noodle, right? It's going to tell you, okay, if you put a constant torque, which you would, T, with one hand, you're going to know the length between both of your hands. You know the shear modulus of that noodle material, right? And then the polar moment of inertia of that noodle, right? It'd be a solid circle, and you could figure it out as pi over 2 times r to the 4th, right? It would give you how many radians did your hand rotate, okay? If you wanted to know how far your hand rotated, right, you would take that radians and you multiply it by the radius of the noodle, and you could tell in actual length, right, how far your hand moved. So a little bit different, okay? So it's only valid for, as I mentioned, right, constant G and T, right, constant shear modulus, constant torque. Our shafts have to be prismatic, right? So diameter and or our polar moment of inertia are constant. Over the length, right? They give us some other equations. That little guy's phi. Yes?
If it was, say it was like split up into two different materials, like a rod was split up into two different materials.
Yeah, you need to have constant shear modulus, G, which is attached to the material, right? So if you have constant shear modulus, then this equation will work. So if you had...
What if we did it twice and like used...
You could.
Okay.
You could. Over the length in which you calculate.
Okay. So like we split the length into two
Yep.
different-
So like one big thing would be, like if you had, this was a collar and we had a shaft that was running down here. We have another collar sitting here and another collar sitting here, right? And say we wanted to apply a torque. We're going to apply a torque maybe this way here, and we're going to do something like this in the example, okay? Where we have a number of different torques coming and going along this shaft. They might come and go from electric motor that implies a, power to this shaft, okay? And then we might have gears or pulleys with belts that are taking power away as we move down this shaft. Well, this shaft could be a solid shaft. This shaft could be a pipe, right? we could calculate what the angle of rotation is, say between this point and this point, based on having a constant G, a constant J, right? Across the length, constant torque across the length. Okay. If you wanted to split it up further and say you welded two different pipes together halfway through, right? You would have to essentially look at this point to the end of that shaft, and then you'd have to start at that end and then work your way further. So this equation only works for a given length of constant torque, constant shear modulus, and constant polar moment of inertia. So they give us a number of other variations of this equation. Don't mind the color, I just so you can calculate that rotation, right, in radians in a number of different ways by making different substitutions in this equation. Okay, I won't bore you with the details of how to get to these, but just know that there are other versions. If you were given, say, the strain at some radius rho, right, and the length of the shaft, you can figure out the rotation. Yes.
So the difference between the shear strength rho and the shear strength max? Those two equations from your second one to your third one? You got your shear strength, I think that's rho.
So this is the shear strain of rho, okay? This is shear stress
The
of rho.
shear stress of rho to shear stress of max then.
So this is the shear stress at some given radius, right? So if we go back to, those are effectively the same equations, just rho equals C for the bottom one, which gives you this maximum shear stress.
Or it's just your axis.
Yep. So in one equation you have rho, right, which is the radius at which you have the shear stress of rho. The other one you have our max radius, or the outside of our shaft, C, which relates to our maximum shear stress. No, good question. Okay. Well, let's do an example, okay? In this case, we have a stainless steel pipe, okay, a hollow stainless steel shaft. Our shear modulus of stainless steel is 86 gigapascals, right? Or 86,000 megapascals. It has an outside, they gave us the outside diameter of 42 millimeters, the wall thickness is 4 millimeters, and they tell us that the allowable shear stress in the shaft is 100 megapascals, right? So we already have a number of things. If we go back to our big equations, right? We essentially have all of this information here, right? We have an allowable shear stress, we have a polar moment of inertia that we could calculate based on the cross-section that we were given. And then we also know the maximum radius based on that cross-section. So we could figure out what the maximum torque is. We'll look at that, right? They ask us for what is the maximum torque that may be applied to the shaft. On top of that, they want us to tell them what's the angular deflection at that maximum torque if the rod was 1.75 meters long. Right? Well, if we start by looking at, right, number one, our maximum torque, or better yet, start out with the equations that we know, right? The equations that we know for torsion are the equation that relates shear stress to torque, right? So we've got this maximum torque, right, would be attached to tau allowable times our polar moment of inertia over our maximum radius, right? That'd be the maximum torque. If we go anything over that, right, then we're going to go beyond our allowable shear stress, right? We're going to have greater shear stress. So that using our allowable shear stress is going to give us our allowable or our maximum torque that could be applied. We also know that we have this relationship of our rotation of our shaft, right? Our rotation of our shaft in radians. And that equals T, right? Our torque times the length of our shaft divided by the shear modulus over the length, over J. Right, or polar moment of inertia. So if we're looking for the maximum torque, we're going to need to know our polar moment of inertia. Well, our polar moment of inertia is a function of our cross section. So if we look through, right, we've got this hollow shaft. Yes?
For the J, are we using T max to find J? Is that first equation? Or
So J is a function of our cross-sectional properties. So that would be our radius or our diameter, right? Not both. So we gotta pick one or the other. We're gonna go back up and we're going to calculate what that polar moment of inertia is based on these equations, right? So if we know the geometry of the shaft, right, the pipe or the solid shaft, we can figure these out. So then J can be known. So in this case, because they gave us the dimensions of this pipe, they gave us the outside diameter and the wall thickness, right? So they said big D, they gave us as 42 millimeters. And they told us that the thickness of the shaft was 4 millimeters. Well, that means our inside diameter, right, or little d, equals 34. It's 4 millimeters, right? So you would take 42 minus 4 is 38, minus another 4 is 34. Okay. So that'd be our inner diameter. So if we know that our polar moment of inertia, based on the diameter of a hollow shaft or a pipe, is our outside diameter to the fourth minus the inside diameter to the fourth times pi over 32. So we get pi over 32 times 42 to the fourth minus 34 to the fourth. We end up with a polar moment of inertia of 174,296 millimeters to the fourth. Okay. So we have J. So now that we know J, right, we need C and we need tau allowable. Well, C is our maximum diameter. Well, maximum radius is really just half the diameter, right? The outside diameter. That would be our maximum radius from the center to the outside of our shaft or the material, right? So we've got, whoops, can't really see that very well. C equals big D over 2, or, right, 42 over 2, or 21 millimeters. And we know tau max, right? Or our allowable shear stress. They tell us the allowable shear stress of 100 megapascals. Well, now we can figure out what tau is. So we've got J, we've got C. We said tau allowable equals 100 megapascals, which is 100 newtons per millimeter squared, right? You know that relationship. I went that route because, right, J and C are in millimeters. So I wanted to have consistent units. So now we can calculate, okay, the maximum torque that can be applied to this shaft so that it does not become overstressed is our allowable shear stress, 100 newtons per millimeter squared, times polar moment of inertia, or 174,296 millimeters to the fourth, all over our maximum radius, which was 21 millimeters. If we look at the units, everything cancels out except for 1 millimeter, right? Newtons don't cancel, so our final unit and our maximum torque is really equal to 829,980 Newton millimeters, or 830 kilonewton millimeters, right? Or 830 Newton meters. Same thing. So that's the maximum torque we could apply to a stainless steel shaft with an allowable shear stress of 100 megapascals, a diameter of 42 millimeters, okay? Or almost 2 inches, right? Not very big, okay? So the second question they asked was, what is the angular deflection at the max torque if the rod was 1.7 meters long, right? Almost 6 feet long. We have this 2-inch shaft. It's almost 2 feet long. You apply a 830 Newton meter torque to the end of it. How far is that pipe going to rotate at the end? Well, we have our equation there, right, for phi, or angle of rotation. We know that it's torque times the length divided by the shear modulus times J. Well, we have everything, right? We've got torque, right? We just calculated that. They gave us the length, they gave us the shear modulus, and they gave us the polar moment of inertia. We can just plug along here. Torque, I'm going to say 829,980 Newton millimeters. Our length, they said, was 1.75 meters. Well, everything in here is going to be in millimeters, so I'm going to swap that out for 1,750 millimeters. Divide it all by our shear modulus, we were told, as 86 gigapascals, or 86,000 megapascals, which we know are newtons per millimeter squared for megapascals. And then finally, we have our polar moment of inertia, which we calculated as 174,296 millimeters to the fourth. If you look through this, newtons cancel, millimeters all cancel, right? Millimeter squares go back up on the top. So we have millimeters to the fourth over millimeters to the fourth. So everything cancels. We get unitless value, which is in radians. We get phi equals 0.097 radians. If we wanted to figure out what that is in degrees, right, we would say 0.097 times 180 degrees per pi radians. And we would get phi equal to 5.5 degrees. Any questions there? Yeah.
Are you picky on radians to degrees when you want to answer?
I guess I'd probably stick to radians first. If you wanted to get maybe a little bit more of a feel for it, when I list off 0.097 radians, it's kind of hard for me to say, okay, that's 5.5 degrees, right? So this kind of helps me visualize how far that would be. In this case, right, not very far. 5.5 degrees is not very far. If you wanted to know, right, we have this shaft. And it rotated, right? If we were standing on the edge of this shaft, and then it rotated some amount, right? In this case, we have our phi. Right? So the end of the shaft, it rotates, right? If I was standing there, if you wanted to know what distance you moved, right? What is this distance here? It would be phi, right, in radians times our radius r, right? The big R to get us out to the outside of our shaft. And then we could figure out, okay, how far did we move? And this plays a lot into mechanical systems with respect to displacements, right? If you had a shaft that had a gear at the end of it, and that gear needed to mate up with another gear on another shaft, right? If you had too much torque applied, right? Or the geometry was such that it wasn't stiff enough, say your polar moment of inertia was very small, right? That gear could rotate too far and go out of misalignment with another gear that was on another shaft, right? See, that's where this plays into the real world of figuring out, okay, how do we mate these two shafts and make sure that the teeth, right, are always in alignment based on the applied loads to each of those shafts? Because one shaft might have an applied torque that's twisting in one direction. The other one might twist it the other direction to the point where, right, the teeth don't line up, and then you no longer have nice mating of surfaces, okay? Okay, we'll go through example 2 on Friday. I will throw out the homework, okay? It'll be due next Thursday, all right? And we'll have a quiz next Wednesday through Friday also, okay? Same thing as we had last week.